In the last few video lessons, we were applying Faraday's law to determine either the amount of induced EMF or induced current or something along those lines for a few particular cases in which flux is changing. And so I've illustrated these problems once again. In one of the problems, we had the slide wire generator, and we were able to calculate the strength of the magnetic field that was required to induce a particular current in this resistor R, but we didn't answer the question of what's the direction of that induced current if the rod moves to the right. So maybe the easiest way to answer this one is to figure out in what way would induced current satisfy Lenz's law, or in other words, would a clockwise current oppose the change in flux that induced that current in the first place, or would a counterclockwise current be required to oppose the change in flux? So let's think about this one. As the rod moves farther to the right, there'd be even more flux now pointing into the page. So to oppose that, some magnetism should be induced that points out of the page, and that's only going to happen if the current's going in a counterclockwise direction in the loop, which means it's flowing down through the resistor. Another way you could answer that one is to think, I know there's got to be a braking effect, so some force is going to have to show up that points to the left. So in what direction would current have to flow in a rod that sits in a magnetic field pointing into the page so that I get a force pointing to the left? So if you face your palm to the left and put your fingers into the page, your thumb points upward and says the current in the rod has to flow up, and that's also consistent with a counterclockwise direction. Another way you could answer that question is think of the way in which the free electrons are going to respond in this rod. So if I draw a few little dots here in this rod, as it moves with a velocity to the right, then the electrons are forced to drift downward. So if I have a drift velocity of electrons downward, that's consistent with conventional current flowing upward, and so no matter which method you use, we agree the induced current is going to be counterclockwise in this loop. Okay, we had another problem in which the induced EMF was all about not so much having a rate of change of area, as this problem suggested. Here, the area of this loop of wire stays constant, but the magnetic field is changing in time, as given by this graph of magnetic field strength versus time. So we have three regions. A portion of this graph where the magnetic field is increasing, a second segment of the graph where the magnetic field stays constant, and then a third segment where the magnetic field is decreasing. So during the time in which the magnetic field is increasing, let's see, the magnetic field lines are already pointing into the page. So if those are becoming greater and greater in magnitude, then there has to be, by Lenz's law, some opposition to that. So to create some induced magnetic field that points back out, just like our previous problem, I think you'd agree that the induced current is going to flow counterclockwise while the magnetic field is increasing, as suggested by segment 1 of the graph. Then, once that amount of magnetism reaches its peak value and stays constant, then there's no longer any change in magnetic field at all, so no change in flux, and so there's just no current at all. And then, as the magnetic field starts to decrease, so it still points into the page, but it's becoming weaker and weaker and weaker, Lenz's law says there's an opposition to that loss of magnetism going into the page. So to restore the magnetism into the page, the current would flow in a clockwise direction. So for region 1, counterclockwise. For part 2 of this graph, no current. I equals 0. And then in region 3, clockwise. Okay, then we saw another problem where there was a steady amount of current flowing to the right through this wire, and then a loop of wire was pulled with a constant velocity along the positive y-axis. So right now there's a little bit of magnetic flux pointing out of the page, right? If you use the right-hand rule and try to illustrate the magnetic field lines, I think magnetic field lines go down like this, then they point in, then they wrap around behind the wire, and here they're coming out of the page. So there's magnetic field passing out of the page through the area of this loop, but the field is strong here and weak here. So as this loop is pulled into a region where the field is weaker, there's a loss of flux out of the page. And so Lenz's law says we want to restore any loss of flux, so somehow the induced magnetism itself should point out of the page. And so the current that's induced as this loop is pulled with velocity v is in a counterclockwise direction to restore the outward flux. Okay, so when we write Faraday's law, induced voltage is negative number of loops times rate of change of magnetic flux per loop. That negative sign is all about Lenz's law, and Lenz's law is used to try to come up with a rationale for the direction of the induced currents.